In the fold of our home galaxy, the Eagle Nebula is one of the richest of the great star nurseries. Intense stellar winds have sculpted a majestic castle of gas. Inside these giant columns, stars are being born. Yet for the dying stars that set this process in motion, the consequences are grim. Supernovae leave in their wake a range of bizarre objects. Among them, a tiny, dense ball of neutrons.
You form an object that we call a neutron star, which is something that has the mass of our sun, but a radius of only about 6 miles or so. That is a very compact object. Every centimeter cube of that mass has a mass of 100 million tons.
Because of its intense gravity, a neutron star is a perfect sphere with a surface like polished metal.
It has the mass of a star, but it only has the size of a city. And the structure of that matter is that it's like ordinary matter, where there are electrons and so on orbiting around nuclei, but with all the electrons sort of squashed into the nuclei and the particles up close together. So something that we think of as incredibly dense, like lead, is really mostly empty space. And if you squish all the empty space out of it and get the nuclei right up next to each other, that's something that has the density of a neutron star.
The existence of neutron stars was first proposed in the 1930s. It wasn't until the 60s that hard evidence was finally detected. Within the remnants of some supernovae, astronomers detected a presence that pulsed with radio signals.
When these were discovered by a graduate student in England in the 1960s, the supervisor thought that they should not announce the discovery for a few months, partly in order to check that it was a genuine astronomical object, but also because of the possibility that this might be an alien signal. And in fact, the code name for the object in the early days was LGM, to stand for Little Green Men.
Aliens it was not. Strange it was. The Crab Nebula is the shell of the same supernova that caught the attention of so many cultures in the year 1054. Deep within, astronomers found a pulsar, a neutron star that spins rapidly, emitting radio waves. Now, scientists are using the Hubble Space Telescope to zero in on the pulsar, the star on the left. It is spewing waves of radiation that have etched circular patterns in the surrounding gas. Yet some dying stars meet a fate that is stranger still. Nature, it seems, has contrived a monster. Early in this century, Albert Einstein speculated about a star with such intense gravity that absolutely nothing, not even light, escaped its grasp. He at once dismissed this prospect as impossible.
The notion that you could squeeze something without limits, right down to a zero size, was considered basically absurd and offensive. And so there was a sort of temperamental reaction against this idea of total gravitational collapse right through until the 1950s.
What once seemed beyond reason now defines the frontiers of science. Astronomers believe that when a large star explodes, enough matter can collapse into its core that it literally exits the known universe.
If the mass of that core is larger than about 3 times the mass of our sun, nothing at the end can stop the final collapse. Gravity wins the final battle and the thing collapses to form a black hole.
In 1991, astronauts placed one of the milestones of modern science into orbit. The Compton Gamma Ray Observatory monitors high-energy radiation that pummels our upper atmosphere. In 1994, it picked up a sudden eruption in the constellation Scorpius. Astronomers around the world zeroed in on the source. A network of radio telescopes stretching from the Caribbean to Hawaii recorded a rare specter. This is the object that came into view. Matter rushing into it is sending out jets of intense radiation. This week marks the culmination of a year-long effort to study the object. Teams in 8 countries are simultaneously training their most advanced technology on it to discover its true nature. From a telescope in the Andes Mountains in the heart of Chile, the astronomer Charles Bailyn was the first to pinpoint its location. Now he's venturing back to the observatory at Cerro Tololo to prove once and for all it's a black hole.
It's the strange objects that always tell you the most about the universe and about science. So if you want to increase your knowledge of how gravity works, for example, you don't look at things falling on the Earth, which we understand. You look at the really, really strong gravitational fields that happen near black holes. And those are the things where our current theories might possibly break down. Okay, Luis, let's make this slew.
No one has ever proven conclusively the existence of a black hole. If ever there was an opportunity, this may be it.
Okay, all right, so are we guiding?
Yes.
Looming within the dense star fields of our Milky Way, 10,000 light years away, this is the brightest and most spectacular object of its kind. What's more, it's not alone. A normal star circles the object in a dance of death. Gas from the star flows into the object through a disk, while jets of radiation shoot from its poles. So powerful is the object's gravity that the companion star's shape is being distorted and squashed, causing its appearance to dim, then brighten as it makes its orbit.
As it goes around the black hole, we're going to start seeing it edge on rather than side on, so you see less of it, and so it's gradually going to get fainter, because in the time we're watching it tonight, it's going to go from almost side on to almost end on. But that one definitely has promise, don't you think?
Though
Okay,
Bailyn and
so
his
that's
team can't
where
view the
this
object directly, they can study its companion.
If you remember, in Alice in Wonderland, there is the Cheshire Cat. The Cheshire Cat disappears from view and only leaves its smile behind to be seen. Black holes have this property. They disappear from the eye, but they leave their smile behind. They leave their gravitational force behind. And it is by that that we then see them and are able to infer their properties.
And then where's the bright star? Is this it?
To prove that his subject is a black hole, Bailyn must measure its mass at least 3 times our sun. The only way he can do that is by studying the effect of its gravity on the motion of its companion.
It takes 2.5 days to make it all the way around, and in order to get that far, in that amount of time, it's got to go at several hundred kilometers a second. And so during the time we're going to be observing it tonight, that's about 15,000 seconds, so it will have gone over 1 million kilometers traveled through space in the 5 hours we watch it tonight. Okay, so now let's zoom up on it.
With its every movement, the star reveals the nature of the object that shadows it.
On the first night we were here and getting brighter. And then on the second night, we were down here at the minimum, and sure enough there was a minimum and it started to turn around right at the end. And sure enough, the first point comes in just where it's supposed to.
Balin has studied the companion star before, but only during a blinding outburst of radiation. Now the flares have died down,
These two guys.
leaving it exposed in stark relief.
Right?
Okay, I see
Okay.
it. It's this.
And now,
Yeah?
Allah.
So here's the star right where the cross is. And that star is different from all these other stars. All these other stars are perfectly ordinary stars, just like the sun. And this thing here is a double star with a black hole eating its companion. And that's what we're going to be watching for the whole rest of the night here.
A lot of people have trouble trying to visualize the nature of a black hole. They know it's something that's greedily sucking in material. It's something that if you fall into, you can't get out of again. And the question is, how can we make sense of all this? How can we, human beings with our limited imagination, try to get some sort of common sense handle on the nature of the black hole? I think the answer is you can't. That these are circumstances where space and time is so warped that it's entirely outside of any sort of human experience. So the only way we can come to understand objects like black holes is through mathematical exploration.
A handful of numbers, some morsels of data. In a scientist's deliberation, one of the strangest phenomena in nature plays out. A black hole contains the mass of at least 3 suns collapsed to a point too small to measure. This is a realm gravity has severed from the rest of the universe.
So we should probably do an observation.
For 5 painstaking nights, Balin has kept vigil.
So we're going to do.
He has found that the object he's studying is massive indeed, weighing in at 7 solar masses. It is, with little doubt, a black hole.
I like to see these numbers come out on the page, and it's a sort of a combination of doing puzzles with doing a kind of profound philosophical thing. What happens inside the event horizon of a black hole is essentially unanswerable in scientific terms, because we are talking about matter falling out of the universe. And so you come right up against the edge of what science can tell you about the universe and what it can't. And I think that that boundary is where philosophy and religion and all these other kinds of thoughts come into contact with science. And that's an exciting thing for me.
The black holes Balin studies may number in the millions in our galaxy alone. But they are by no means the ultimate showcase for gravity's power. In the heart of the M87 galaxy, 50 million light-years from Earth, gas swirls into a truly massive black hole and glows as it heats up. Astronomers clocked the speed of the gas as it circles around and measured the black hole's mass at more than 2 billion times that of our sun. The ancestors of these giant black holes inhabit regions at the limits of our vision, a class of objects known as quasars. They are powerful beacons that take us back to a time when gravity began to draw gas into the first galaxies. A quasar is the product of a massive black hole in the center of a galaxy that is swallowing huge volumes of gas and stars. A flood of blinding radiation erupts.
Not only is this an interesting process, the notion that we could have a black hole of 1 billion solar masses shining more brightly than 1,000 galaxies, that's pretty wild. But these are signposts. These were a phase in the lifetime of infant galaxies, and we can see them to great distances. So they are beacons out there at the edge of the universe showing us when galaxies first began to form.
In time, as they consumed their fuel, quasars like these grew dim. But the black holes that powered them remained. Today, they are thought to loom at the heart of many a galaxy, including our Milky Way.
There are two reasons why black holes are important. One is because it's increasingly obvious that they play a major role in shaping the universe, both at the centers of galaxies and as the remnants of burnt-out stars. And we still have yet to learn a lot about them. But there's a deeper reason, I think, why they're important. The black hole conceals something which is very profound, which is often given the word singularity. This is like an edge or a boundary to space-time. It's a point where space and time, so to speak, come to an end.
As we look out into space, we probe a universe we can see, one whose matter emits light strong enough for our telescopes to record. But there is another side to our universe, one that has evaded our detection. In fact, fully 90% of the universe is unseen and unidentified. Astronomers call it simply dark matter. Mysterious particles, countless burned-out stars or black holes. Whatever it is, dark matter is out there.
There's probably more dark matter than there is visible matter, but we really haven't much of an idea as to what this dark matter is. There are a whole lot of candidates, maybe 30 different types of things that the dark matter might be, and of course it could be more than one of them. And I think that is the most urgent question that we must try to answer. What is the dark matter?
In fact, I think we might have some pretty clear skies at the beginning.
Went from 22.6 up to, we think now, about 22.4.
But it might have been on the
The
rise.
skies have opened, and now the data begins to roll in.
Well, that's an obvious one at redshift 0.45.
Yeah, look at that.
We're completely destroying these things.
Wow. That's great. Oh, now we can
When
start
the
saying where
weather
it
is good, no one can compete with this telescope.
Tonight, they're making up for lost time.
Supernova should be coming up right about now. There it is.
That's
It
nice.
is. It's a supernova. Look at all the undulations.
Yep.
We got another one. Oh, man, this is like shooting fish in a barrel, you know? Oh, fantastic. Oh, there's one. Yeah, there's a bit of a calcium one. You fluxed
Deep down
Yeah,
inside,
if you look at the pictures here,
the reason many of us are scientists is to experience the thrill of discovery,
before going up.
Right.
to sit there one night observing and to come to a realization that you're the first person in the world to have understood that particular phenomenon. There's something really gripping about that, and it's something that all scientists who have made a discovery never forget, ever in their lives.
Okay, there's H
that
and
looks like
K.
H and K, so
Yeah,
that's-
let's see what it'll turn. Looks pretty high to me.
Okay, that's
Wow.
65,
So let's
50, 39,
see what this
60.
give us.
0.65.
0.65. Hot dog.
So
That is
explains,
higher.
that explains
Oh,
what's
boy.
past, where we've gotten these
Yep.
charts for. So
Oh, if this is the case, then it beats our 0.61 record.
for this one,
The other calcium line gives the same redshift, so we've got a new record.
We peer into deep space searching for clues to its most profound mysteries. The nature of supernovae, the extremes of black holes, the puzzle that is dark matter. These wonders are steadily yielding to our gaze.
The most personal thing that I have taken out of this is this incredible sense of belonging, of having one great river of time, from the birth of the universe, the quantum fluctuations, the formation of galaxies, which made possible the formation of stars, cooked heavy elements, supernovae that shed heavy elements like carbon and oxygen into the interstellar medium, later swept up into the solar system, makes planet Earth, makes organic matter, makes human beings, makes me. It's one very beautifully integrated story from beginning to end.
Today, that story is unfolding still. Exactly how it will end remains a mystery. Our own lives are simply too short to witness the grand transformations of the universe. Often, though, in events visible across the depths of space, we gain fleeting glimpses into its true nature. We scan the firmament, brace ourselves for what it will tell us.